Hello, good morning, good afternoon, good evening, depending on the time zone. I'm here in the Pacific time zone in the US. So it's a little bit early, but that's okay. I made sure that I'm extra awake for this presentation. I'm really excited to be talking to you all today about NLP. NLP is NLP is a really hot topic these days. We've seen a lot of media coverage. And I wanted to talk to you a little bit about some tips, techniques, and tricks that all of us can use and learn from these massive NLP models. Just a quick, by way of quick introduction, I'm a director of recommendation systems at Twitch, which is the premier live streaming platform. We are very well known for streaming games and music and a bunch of other live streaming use cases. Prior to Twitch, I used to work at Twitter. I used to lead the recommendations team along with the trends team and the explore team. I've worked at Capital One, Gale Partners, and a bunch of different companies. And I've been doing recommendation systems plus NLP for the past 10 years or so. Recently published my book as well. The book is called Advanced Natural Language Processing with TensorFlow 2. And I believe there is a giveaway at the conference for this book. So hopefully some of you will get lucky and win a free book. So let's get started. If you have followed some of the media coverage in the past few months or so, big NLP models are making lots and lots of headlines. The latest entrant in this is GPT-3. GPT-3 is a model that has over 175 billion parameters. And all sorts of things are being used. It is being used for all sorts of things. I've seen people show code examples where they are generating HTML code or SQL queries from English and so on and so forth. This picture here, I hope it's readable for you. It's just trying to contrast the size of the various models. At the very left, you have Albert Base with about 12 million parameters. And on the extreme right, you have GPT-3, which is about 175 billion. GPT-2 by comparison was 1.5 billion. And BERT, which does quite well, the BERT base model was 110 and the BERT large was 340. Since the transformer architecture was introduced, Since the transformer architecture was introduced in 2017, the size of the models has been increasing. The transformer architecture was very, I think, revolutionary in the sense that NLP was not making the same kind of progress that we have been seeing in computer vision. But with the transformers, the performance has been amazing. However, once you have very large models, you need equally large data sets to train. So that's, I think, one area to think about. Training such models obviously takes a much longer time than other models. In this case, there is some estimate from the Lambda Labs folks that the cost of training GPT-3 on today's cloud providers would run into about $4.6 million. And if you were a researcher, probably you will not train GPT-3 in only one go. You would have probably trained several iterations of it to get to the final version that you see. That could be prohibitively expensive for small firms, medium-sized firms, and startups. So there is some concern about, are these models over-parameterized? How easy or difficult it is to train? And the purpose of this talk is to give you some pointers, having gone through some of these models, whether it's T5 or GPT-3 or Pegasus. There's a bunch of different NLP models that are being trained, and see, is there a set of things that we can do that even if we don't have the huge data sets, even if we don't have that much compute, can our NLP models still work? There's a number of questions that we should probably think of. The primary question that I'd like to address is building larger models the only way forward? I'd like to think not. And the reason that I'd like to think not is that I feel that if that was the only way, a lot of the industry would just be like unable to move and make progress on NLP, which is not ideally the case. There is a way, and there are tips and tricks which can make even smaller models work better. There are a bunch of other questions that we have, some of which we will cover in this talk and some not. One question is, how many such models do we really need? Like, do we need multiple GPT-3s from various corporations or startups? Or do we need just one or two, like BERT and GPT? Is that enough? Probably that's one question that we will leave for you as the audience to think about. Is the large number of parameters really behind the performance? We'll get into that. And there are two other questions. Where do we get such large data sets, and how do we ensure quality of such large data sets? The last question I'll just briefly touch upon. It's a question that is beyond the scope of this presentation. But once you create and collect very large data sets, quality becomes very important, especially if the source of your data is scraped from the internet. If you scrape content from the internet, it is possible that the content is either biased in some way or not really representative of the population that we are trying to serve. So we have to ensure that we are thinking about properly where we get these data sets from. But how do we get large data sets? I think there are some ways that I can discuss later in the presentation on how to be creative about getting data sets. All of the tips that we are going to talk about are actually found in various papers, whether you read the Transformers papers, attention is all you need, or whether you read the BERT paper, or there are 3 GPT papers. The main architecture for GPT is in the first paper. Other GPT-2 and GPT-3 are basically the same architecture with different hyperparameters and different data sets. So as I was reading through these models, I realized that every model, when it publishes, it publishes on the basis of beating some benchmark or getting a state-of-the-art result. However, some very basic things, if the model does it differently, the performance drops significantly. And this leads me to believe that the model size is not the only reason that these models are doing so well. There are a bunch of other reasons that all combine together to get them to the state-of-the-art results. We will cover a couple of these in detail here. Tokenization and handling out of vocabulary words is a very important thing. Tokenization is the process of dividing up a sentence or a paragraph into individual tokens that we will feed in. Truncation schemes, we will cover that. Creating self-supervised training data sets, we will cover that, because it's very important if you want to train larger models to be able to access larger data sets. The last one, learning rate annealing. I don't technically cover that in this presentation, but that's a fairly straightforward concept. If you are training your models for a very long time, many of these models are trained for days at an end. I believe BERT was trained for 3 or 4 days at the time it came out. The learning rate itself needs to be adjusted so that you don't oversaturate, so you don't overshoot the minima. If you overshoot the minima, what you will see is a graph where your loss is decreasing, and then suddenly it starts shooting up, and then it will start decreasing again. That is not what you'd like to happen. And it is invariably happens even with Adam style optimizers. So in most of these models, if you look at the learning rate graph for the first 1,000 or so iterations, they are sometimes up to 4,000 iterations of training. the learning rate is actually increasing. And this is why main reason is large gains in or large decreases in loss are obtained in the first few cycles. By taking large steps or large learning rates towards the minima, we can reduce the training time. And then after the 1,000 to 4,000 steps, we see a linear decline in learning rates, right? So that's learning rate annealing. You can read up more about it. I cover it in detail in my book as well. But let's talk about some of the other ones. So tokenization. In NLP, and I contrast NLP with this with the computer vision here. In computer vision, there is very little work that needs to be done per se to take an image and look at and pre-process it or process it for a network. You may want to do some averaging and mean shifting and stuff like that, but the individual pixel has the information in a way that the computer can understand. And what I mean by that is, for the 3 channels, if you have a color image, the image already has data in numerical format. However, that is not the case for text. So there is a lot more work you need to do. Essentially, you need to tokenize, which means creating a vocabulary, almost like a dictionary, where every word that occurs in the text, or the better way of saying it is every token that occurs in the text, needs to be assigned an ID. And we are going to perform learning on that ID. Essentially, the models don't really understand what is going on. They're just using these IDs to learn embeddings. It's fairly, one simple way as displayed is to do word tokens in English. Most of the Latin languages, many languages use spaces to distinguish words. You can also do character level tokens, but it is not a solved problem in other languages like Japanese or Chinese. In German, you can have compound words. So what happens is, if you just use spaces for tokenization, there will be out of vocabulary words because you will be constrained by how many words can you have in the vocabulary. I did a simple test with the IMDb dataset and the GLOVE vectors. GLOVE vectors have a vocabulary size of 400,000. In the IMDb dataset, what I realized was about 18% of my tokens were out of vocabulary, meaning that even though I had 400,000 words in my vocabulary, there was about 18% of the input tokens couldn't be matched to an item in the vocabulary, which is significantly going to reduce the accuracy that I can get from such a model. A core innovation here was using the word piece or BPE tokenization scheme. So if you compare BPE to GLOVE vectors, a vocabulary size of about 32,000 tokens is sufficient to have 0 out of vocabulary words. How does BPE work? Let's take a look at that quickly. BPE is a technique that has its roots in information retrieval. I feel personally that this is the unsung hero of modern NLP methods. It eliminates out of vocabulary words, and it is able to handle text with arbitrarily large vocabularies. What we are trying to do is we are trying to repeatedly take a sequence of text and find longer and longer sequences that this are subsequences that this piece of text is built upon. It's almost like a coding problem that you get when you go and apply for a company. So, but it's a very fun algorithm. It's fairly straightforward. Hugging Face and also TensorFlow and PyTorch also implement this. So you can take a piece of text or a corpus and train a BPE encoder on it and also persist it to disk. This is all covered. Truncation schemes. So for truncation, which of these words do you take? Every model has some length limitation on how many tokens that can be taken in. These lengths have been increasing. Today, about 1,000 tokens can be taken in, but there is always some limit. A smaller model takes in smaller lengths, possibly. because that has an implication on how many a model, what is the size of the model. Let's take two examples, which is a review of my book from Amazon. I just pasted this review. If you were to do a sentiment analysis, just think for yourself whether the first 30 words or the last 30 words would give you better sentiment analysis. Generally, the last 30 words might be better, or the first 30 words. Now, what happens if you do the same thing in Arabic? Arabic is a language that goes right to left. So we are traditionally used to thinking in the NLP world mostly in terms of English. I converted and translated the same review that you see here through translate.google into Arabic. So pardon me if the translation is not great. But the point here is the definition of first 30, last 30, left or right will also change. So these are things that you should be thinking about when you are building your models. And yes, by default, use BPE encoding schemes. Don't use word tokens. Now, the last part that I want to quickly go over is self-supervised training and transfer learning. We have talked about training large models into requiring large amounts of data. Now, in text, we are fortunate that there is lots of text because digitization has produced a lot of text over the decades. The biggest challenge is we don't have enough labeled data. So there is a bunch of techniques that folks have been using, and I feel another huge contribution of these papers has been the creativity that the scientists have shown in converting unlabeled text into labeled outcomes. As an example, in the BERT paper, they have invented two ways of converting an unlabeled data set into a labeled data set. The first one is masked language model, or MLM. What they do is they take a sentence, they arbitrarily mask, or I should say randomly mask 15% of the tokens in that sentence. So if you have 15 words in a sentence, you mask one word. You can play around with that. And then they pass it through the model and ask the model to predict the masked word. Now, in this scheme, note that no human has to label the sentence. And every time you pass the same sentence through, your randomization scheme will will produce different amounts of training data. It's a very creative way. Another model that is used is next sentence prediction, NSP task, where they take a pair of sentences from a paragraph. So the second sentence succeeds the first one. They input the first one and they ask the model to complete the second sentence. In Pegasus model, which is a summarization model, they are trying to do. They've invented this gap sentence generation. It masks entire sentences from the document and concatenates these masked sentences as a summary with some logic to say what is going to be a good sentence that could be acting as a summary using some statistical methods. And then they get world-leading performance on summarization. These techniques you can also use in your everyday life if you are building NLP models. This can actually, maybe if you have massive amounts of data, but you're because of them not being labeled, you are worried about how do I use it in a model. Maybe this is inspiration for you for your day-to-day models. And so just to quickly summarize, and I'm happy to take questions if there are any. Big NLP models seem to imply a lot of small things that can have an outsized impact on performance. In fact, I would argue that without BPE, none of these models would be able to get to the level of performance that they're showing. Many of these tricks that I've just shown can work for any NLP model. And in fact, large models can be beaten by a small task-focused model with enough domain-specific training data. So I don't want you to ever think that because your model doesn't have the number of parameters that a GPT-3 has or the type of training resources, your model will not perform better. In fact, for a specific domain, it might actually perform better and outperform any of these big models. So don't underestimate the power of a domain-specific model. With that, I turn it over for for questions or comments.